So when we're looking at whether or not to do the small x approximation, we've normally been looking at just one of these. And it's usually the side that's not going to change very much because I'm shifting this from the left side to the right side. So we would normally look at this 0.1 minus 2x squared and say, okay, I can use small x approximation there because this equilibrium favors, that's not what I want to do. This equilibrium favors my reactants, so that's not going to change very much. But what about this other x, 0.1 plus 2x? Can I assume that that's also going to be small?
Yes, because the reaction favors the reactants. There's not much going to the right side.
Yes, there's still not much going to the right side. Yes, that's one way to think about it, is this probably isn't going to shift very much. The other way to think about it is that if subtracting 2x from 0.1 is an insignificant change, a negligible change, then adding 2x to 0.1 is also going to be negligible. And so I can actually drop both of those and assume that the change is not going to be big enough to matter. So this will be 0.1 squared times x over 0.1 squared and that's a lot nicer to work with. Oh, there's another fun simplification thing that we get to do here. Anything else I can cancel out? Yeah, 0.1 squared, 0.1 squared. I couldn't do that before because I had plus and minus. Not the same thing, but if I drop plus x or minus x, these are both the same thing now. So x equals 1.67 times 10 to the negative 7. Sometimes math is just great. So now when I plug these in, I mean, this is, well, we should check. We should check, right? Depending on how quick you are with math, you don't even really need to check because 1.67 times 10 to the negative 7, right? So we take our x and we divide it by whatever we're going to be adding or subtracting it to or from. Is that going to be less than 5%? It's going to be less than like 0.005%. So we're safe. You divide those, you get a number that's real small. So this is going to be 0.1, this is going to be 0.1, and this is going to be 1.67 times 10 to the negative 7. Because even if we did go in and subtract that, multiply it by 2, subtract it, we're going to end up rounding back to 0.1, almost definitely. Questions? Okay. Okay. I was thinking about changing this one, but this is another good example of. So we can start off just doing the regular thing where we say I've got some concentrations for things. I can plug those in. Get my initial going, the change. The end or equilibrium. So how do I know, again, that I can do a small x approximation? K value is super small. And most of the time, that's all we have to worry about. Sometimes, though, this is something that there's a previous question. I'll just, because it wasn't that far ago. No, it was actually after this. Like in this question, that's why I brought up that Excel sheet. Most of the time, we just have to worry about the magnitude of K. But sometimes, if our concentrations are also really small, we do need to think about, well, if I have a really, really small value, even if the change is going to be small, it's going to be a larger percentage of a smaller value. So if I'm starting with not very much already, then the amount that it changes by has to be exceptionally small for me to be able to assume that X is negligible. And I think on this question, because we're starting out with 1 times 10 to the negative 4, our K value is 1 times 10 to the negative 7, which is a very, very small K value. But it's only 3 orders of magnitude away. So it might be on the border of working. That being said, usually doing the math with the small x approximation, you're going to end up saving time anyway. So this is going to be okay. This is going to be it's 4x squared times x. This is 4x cubed. 1.00 times 10 to the negative 4 equals 1.67. Oh, yeah. So now this is not especially hard to solve. Oops. There you are. Times 1 e negative 4 squared. Oh yeah, because it's going to be, this is 4x cubed equals divided by 4. And then we need the cube root. If your calculator doesn't have a cube root, it's the same as raising it to the power of 1 divided by 3. So x is 7.47 times 10 to the negative 6. And then if we do 1.00 times 10 to the negative, wait, I should do it over here. 7.47 times 10 to the negative 6 divided by 1.00 times 10 to the negative 4. Dang. Times 100, 7%. There's an additional problem that you'll run into here because if we don't end up doing some kind of approximation on this, you're going to end up with a third order polynomial, which there's not like a nice quadratic equation that I know of for that. The TI-36X Pro has a solver for third order polynomials. Other calculators will have just a general solver, and you could use that. In this case, though, what we can do is we can take this number that we got for x, and we can plug it back in. Say 2x, oops. Actually, do it at this point. So 4 times 7.46 times 10 to the negative, actually, no, not there. 4x cubed divided by, and then we plug it in down here where we were approximating. 2 times 7.476, 7447 times 10 to the negative 6. Square that whole thing. (1e) negative 4 minus 2. Oh, I need parentheses around all of this. 2 times 7.47 e negative 6. Square that times 1.67 e negative 7. Divide by 4, raised to the 1/3. (6.71) times 10 to the negative 6. Divided by 7.46. That's probably good enough. Otherwise, you take now this new number and you plug it back in just like we plugged in that one, and you do it again. And then you'll come out with a number that's even closer to whatever the correct value is. And in lab on Tuesday, I said you could repeat that until you get a change that's less than 5%. Here we're at 10%. On like an exam, I'm not going to give you one that you have to do this many times. This is too many times. This is too much. If you can show me that you could do it once, I don't need you to show me that you could do it 3 times. If that makes sense. And so we can basically continue to approximate until we end up with the same number. I ended up on Excel doing this in an Excel sheet, and then it continuously plugs in the number because I wanted to see how many times on average you have to do it before you basically converge at the same number. And honestly, after 4 times, it's changing in like the millionths place. So 2 times gets you really close, 3 times gets you really, really close. After 4 times, you're just kind of wasting time making smaller and smaller changes to your number. Eventually, you end up, after like 15 times, I think Excel runs out of like floating point values or something because they're exactly the same. So at most, you need to do this like 3 or 4 times. On a test, I wouldn't make you do that many times. Other questions about what I did there? Why I put numbers where I put numbers? I'm trying to talk about just the parts that aren't the algebra and just the math. Okay. Oh, and then we got to go back and plug that in. at some point you reach a Zen flow state, do these enough times, and it's like, ah, yes, I know what to do. I know where to go. I've walked this path many times before. And to walk it again is like walking with an old friend. Oh, this one would be, I guess, 3 sig figs. So just know I'm never going to make you do a higher order polynomial than a quadratic. Second order polynomials, that's it. If you get a third order polynomial, you need to approximate somewhere. If you get a fourth order polynomial, you definitely need to approximate somewhere. There's not, well, you could solve it exactly, but it's not easy. Okay, so let's go onward then. When you're doing equilibrium isotables, concentrations must be expressed in moles per liter if you're using concentrations. Partial pressures have to be in atmospheres. Sometimes you can use moles instead of, so moles may be used in place of concentration or partial pressure, but only when the moles of reactants in the chemical equation is equal to the moles of products. If they're different, then you can't do that. The and the small x approximation does not mean that x is 0. It means that it's small enough. Think about it this way: the x is small enough that with sig figs, the x doesn't matter. It is changing things. There is a concentration change, but it's small enough that we can't detect it beyond our sig figs. So we can ignore it. All right, now Le Chatelier's principle, which we've already done the lab for, so a lot of this should already be at least somewhat familiar. In Le Chatelier's principle, or I should say, Le Chatelier's principle is that when an equilibrium is disturbed, the system shifts in the direction that minimizes the disturbance. Actually, we'll try this. I need a volunteer. John. So stand here. I'm going to push you a little bit. Right? So if I push John, right, he's trying to resist that disturbance. Our equilibrium, thank you, John. That's it. That was all. Right? But that's what you're doing. That's the disturbance. You add something, you change an equilibrium, it moves, and then tries to come back as much as possible. So a system at equilibrium tends to stay at equilibrium or bounce back towards the equilibrium as much as possible when disturbed. So I think concentration change is probably the easiest place to see this. If I add in products, the reaction shifts to the left. And that's because, well, in terms of the math, if I add to the products, I now make Q greater than K, and it shifts to the left. Because if Q is greater than K, I have too many products. It'll shift left to reestablish that equilibrium. So adding products, increasing the rate of the reaction. If I add stuff to the reactants, it does the opposite. Now I've made Q smaller than K, and it shifts to the right. And I think this is where this simulation shines, because we can see that if I add concentration to my reactants, I've created a huge disturbance in the amount of reactants. And so the equilibrium is going to shift back, and it's going to try to get back to close to this number. And as it goes down, then this is going to go up but eventually they'll level off. So there's a huge jump, and it slows down. And the reason it slows down is, I mean, again, we personify a lot of chemical reactions, but the reason that it slows down is not because it wants anything, right? These don't have feelings. It slows down, or it comes back to an equilibrium because by adding to the reactants, I increase the rate of reaction. And then as those reactants drop, that forward rate decreases while the reverse rate increases. And then that keeps happening until they meet at the same rate where equilibrium is established. So this was kind of the inspiration for making that. Right, so disturb equilibrium by adding it to either reactants or products. That spikes the concentration, which spikes the rate. And then since that rate's faster, now it's moving more over towards the products over time. I guess that's added to the products, moves it over to the reactants, which speeds up the rate of the reactants until the rates are the same. So increasing concentration of reactants causes a shift towards the right. Increasing the concentration causes a shift, or concentration of the products causes a shift to the left. And then decreasing is just the reverse of that. And if we think about it in terms of rates, which I can't do in the simulation, we can figure that out. If I decrease the concentration, I decrease the rate. So I kind of create this hole that then the reverse rate, did they do that here? No, these are both increasing. Yeah, so if I decrease the concentration of the reactants, now the reverse reaction is faster than the forward reaction because I decrease the rate of the forward reaction. And so the forward reaction will be faster, but because it's faster, it's decreasing the concentration of the products, which increases the concentration of the reactants, and they again meet at the middle. So if I take this reaction and I add bromine to the mix, which way is it going to shift? Not all at once now. Am I adding a product or a reactant? Product. So which reaction rate have I increased? The reverse. So which way does the reaction shift? To the left. So what's the effect of adding additional BrNO? Just to the right. The reverse rate goes up. Reaction shift left. If I add to the reactants, it's the forward rate that goes up, and the reaction shifts right, or towards products. Easy as that. For gases, I mean, these are gases, but we're talking about concentrations. For gases, we often use the partial pressure as a stand-in for the concentration. Or I suppose we can. If the volume of a reaction mixture at equilibrium is changed, so if we change volume, the volume is changed, then the pressure changes and the system shifts to minimize that change. The important thing here, though, is it's not just that the pressure changes, it's that the partial pressures of the reactants or the products changes. So if I have, I'll just use this reaction from up here. Was that 2? It's 2 of those. H2NO plus Br2. So if I have 1 atmosphere of all of these, they're in some reaction vessel. And let's just say that let's make things real easy. This is 1 liter. If I cut this in half, what happens to my pressure? Increases. What happens to my concentration?
Same, right? Well,
Moles divided by volume. Cut the volume in half. It also increases the concentration. So the partial pressure of each of these would go up. And that's going to cause a shift. And part of the reason that it causes a shift is because now I've got all of these increased concentrations, increased pressures, partial pressures of each gas. So like our total pressure here would be 6 atmospheres. And if we look at the amounts of moles here, I've got 2 moles of, I don't know what that is, BRNO. Nitrogen monoxide, I've got 2 moles and I've got 1 mole of bromine gas. This is 3 total moles of gas. This is 2 total moles of gas. And I just disturbed this reaction by increasing all of these partial pressures. And I can get an overall lower partial pressure if I start to convert some of these over here, because I'll have less gas. In a sense, I'm taking the 2 gases and I'm compacting them into less gas, right? If I recombine molecules, then I've got fewer molecules around. So this will shift to the side that has fewer atmospheres or fewer moles of gas. So we're going to think in terms of the partial pressures. Take another attempt at drawing a good cylinder. That was better. Okay, so again, if I push down on the piston, what happens to the volume? Volume increases. Or sorry, decreases. I don't know why I said. You said decreases with the yawn, and I heard increases for some reason. Yeah, no, you're good. I was just like, yeah, sure, that. See, communication's important. And then the pressure increases. And in this reaction, how can I lower the pressure? Which side has fewer moles of gas? Oh yeah, the right does. Right, so shift to the products. Now what if I add helium? Cylinder stays the same, it's the same volume, but I'm pumping in extra gas. How does the pressure change? Pressure will increase if I add helium. So will this reaction shift? The overall pressure changes, but what about the partial pressures of my gases? They're the same. So because Dalton's law of partial pressures was the P total equals the pressure of N2 plus the pressure of H2 plus the partial pressure, right, of all these, NH3. When I increase the pressure by adding in an inert gas that doesn't participate in this reaction, I just add another partial pressure here. And that does increase the overall pressure, but it doesn't change the partial pressures So there's no shift in the reaction. Because it's the partial pressures that determine the concentration of each of these gases. You could also think about this, like I still have the same number of moles of each type of gas in here in the same volume, so the concentration is the same. So remember, if the partial pressures change, then my reaction will shift. But if the partial pressures of reactants or products don't change, it won't change the reaction. We could also think of this in terms of calculating Kp, because that would be the partial pressure of NH3 squared over N, or partial pressure of N2 times the partial pressure of H2 cubed. Again, I'm plugging in partial pressures. If those numbers don't change, and I calculate Q, the number's going to be the same. K and Q are still the same. The book, I don't know, in reading through the book, it didn't do, felt like it skims over this a little bit.
What if you added something that would interact?
Ooh, if I added something that reacted with? Yeah, so like if I,
Hydrogen would react with hydrogen, right?
sure, yeah. If I throw something in here that will react with the hydrogen, but now I've added another equilibrium. And so if I add something in here that uses hydrogen, like oxygen, and I burn it, and then that converts into water, now I have decreased the partial pressure of hydrogen, that will shift the reaction, which would be the same thing as removing hydrogen or adding hydrogen to the mix. But it's an inert gas, so if it's not something that reacts, then it won't change the reaction. Shift the equilibrium. Again, if we do add something that changes the partial pressure, for example, increasing or decreasing volume, because changing the volume affects the partial pressure of everything inside the container, that will cause a equilibrium shift or a reaction shift. So decreasing volume, because it increases partial pressure, it'll shift it towards the fewer moles of gas. Increasing volume decreases partial pressure, so it'll shift towards more moles of gas to reduce or resist that change in pressure. I guess I should point this out. Right? Fewer moles of gas, greater moles of gas particles. If we have the same amount of gas molecules on either side, changing volume also won't change the reaction. So I decrease the volume on this. Does the reaction shift? Yes? No. Yeah, decreasing volume. Volume will increase partial pressure and shift to the smaller number of moles. So in this case, it'll shift to the right. What if we increase the volume? Yeah, decreasing the volume did one thing, then increasing the volume does the opposite. It'll shift to the left because I've decreased my partial pressures, and it'll shift to the left. All right, and I think this is the last thing, but temperature change. The way to make temperature change easier is if you think of heat as a product or a reactant. So in an exothermic reaction, you do the reaction, you get out extra heat. That heat is a product. If you do an endothermic reaction, it's absorbing heat, so that heat is a reactant. We could make this all very complicated by changing pressure, but we're not going to. Because heat doesn't have a concentration, this is at least partly why, if not the entire reason why, changing the temperature changes the equilibrium. So in this reaction, for example, heat is one of my products, but we can't represent that in terms of a concentration. We'll talk about energy and how it factors in later, but in this case, if I increase the temperature, or if I add heat by increasing the temperature, that's my, or one of my products, so that'll shift this to the left, which means this reaction now at a higher temperature will have a smaller K value. It's not the the concentrations will change because K is changing. So if I add heat, K changes. Not so constant now, are you? If I remove heat from the same reaction, then it shifts towards the right and gives us a larger K. And then things can get tricky around this. You have to think about terms like heating or cooling and what that means for the reaction. But overall, just think of, well, and this is for heat as a reactant. So when heat's a reactant, adding heat gives us a larger K, removing heat is a smaller K. K has to change because we don't have a way to quantify heat in terms of concentration, so it doesn't go anywhere in the reaction or equilibrium, law of mass action. It's not the law of energy action. But we'll be able to calculate K in terms of temperature and energy later. Oh yeah.
Like in the test, we got something like this in the lab exam. So if you add like N2O4, heat will decrease.
Oh yeah. So like here, if you add N2O4, yeah, so then if the concentration of this goes up, then heat goes down.
That was right.
So like, yeah, in this reaction, if I add in N2O4, that concentration goes up, then heat has to go down. If I added in NO2, then heat and N2O4 would both go up. So for our exothermic reactions, this change, the shift in equilibrium, is represented in changing K. In increasing the temperature, the value of K decreases. decreasing the temperature, the value of K increases as long as it's an exothermic reaction. In an endothermic reaction, increasing the temperature, K increases. Oh, I should have done these as blue, huh? Value of K increases. Decreasing the temperature, the value of K decreases. This kind of thing is always the worst to memorize because you've got so many things that are increasing, decreasing, decreasing, increasing, 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 decreasing, decreasing. Not fun to remember. Just remember that if I have, let's see, this is, exothermic, right? A in equilibrium with B plus heat. Increasing temperature is adding heat. So it shifts to the left. Decreasing temperature is decreasing heat, so it shifts to the right, which means larger K. This means smaller K. All right, we're out of time. For like 2 slides. That's okay. All right, so this was with regard to temperature change on equilibrium. This reaction is exothermic. So does that mean heat is a reactant or a product? Yeah, it's a product. It's exothermic, it's releasing heat. So heat, we can think of heat as being a product. So if I increase the temperature of the reaction, which way will the reaction shift? To the left or to the right?
But
To the left. So if I increase heat, this will shift to the left. What about decreasing the temperature?
Right.
Shift it to the right. And since we have so much extra time, why does it shift? If K is equal to concentration of the products divided by concentration of the reactants raised to their coefficients. What's the concentration of the heat? It's not in the equation. So why does this shift to the left when I increase the temperature? What changes? Technically, yes. The pressure could change, but for these, we're going to assume the pressure doesn't change. But I'm I'm changing the temperature of the whole thing, so the rates of both reactions will be affected. It is an exothermic reaction.
Add more energy into the system, it has to release more energy.
If we increase the temperature, it'll shift to the left, which means it would actually be absorbing energy. Yeah, if we increase the temperature, it shifts to the left. The concentrations don't change. What am I maintaining? I guess, am I maintaining the same equilibrium? Because I'm adding more heat, and heat is a product, changes K. K changes. If we change temperature, K changes. And even though heat isn't part of the equation, if we think about heat as being a product, then we can kind of think of heat as being in K, but it's really that K will become, or actually, K will be smaller if I increase the heat. Because a smaller K favors the reactants. If I increase the K, or if I increase the heat, then K will be larger. We haven't really talked about, when we talk about thermodynamics, we'll talk about why.
Changing the heat will change K.
Changing the temperature changes K. Which is why for most of the problems, it'll say the reaction is taking place at some temperature, or that K is some value. Actually, is there even an example in here? Well, these are all Le Chatelier's. Nope. Or like here. Bless you. At 800 C. Now, we don't know if this reaction's exothermic or endothermic, so we can't really make a prediction about which way K would change, because if it's an endothermic reaction, then everything's reversed. So another exothermic reaction. What will make this shift to the right? Would A, adding NaCl to the reaction, cause it to shift to the right? No. That would cause it to shift to the left. So it's not that. What about increasing the volume? What? Increasing volume causes a decrease in pressure, which means we'll shift towards more moles of gas. So that's also to the left, because up here I've got 3 moles, and this is 2 moles. So increasing volume would decrease the partial pressures and cause us to shift towards more moles of gas, which would be to the left. And increasing the temperature, it's exothermic, which means that heat is a product, so adding more heat makes K smaller, which will shift the reaction to the left. So none of the above. Or the opposite of all of the above. Removing NaCl would make it shift to the right. Decreasing the volume would make it shift to the right. Decreasing temperature would make it shift to the right. Are there any other questions about Le Chatelier's principle?
Can you explain the
Yeah. Yeah. So we got, is there a particular part of? Yeah. So if you think about like, if I have like a cylinder, and that cylinder, I'm going to move it down here. If I increase this, pull this out, then I have more volume for all of that gas. As long as the temperature doesn't change, that means my pressure will go down because I'm basically spreading out the gas in more space and there will be fewer collisions on the sides of the walls. So the partial pressure of every gas in the container will decrease. And then if I decrease the partial pressures, Kp is going to be the partial pressure of NaCl squared over the partial pressure of NO squared times the partial pressure of Cl2, chlorine. If all of those go down, I guess we didn't really do it this way before. If all of these numbers get smaller, I have more numbers in the reactants that get smaller. And so that side of the reaction's more affected by the pressure change. So I've decreased those numbers, but now I'm multiplying that decrease and squaring that decrease. So it magnifies the amount of decrease. Versus if I had Kp and it was some reaction where it was the pressure of A just over the pressure of B, if I change the volume of this reaction, well, decreasing the volume would cause this pressure to go up, but this pressure would go up by exactly the same amount. If I square one of those, then decrease the volume or increase the volume. This one will change, but this one will change by the square. So it changes even more. So mathematically, because I have more moles of gas on this side, it's more affected by the change in pressure, which means that now my K will be, or I guess it would be Q would be too large, and I'll move from products to reactants to get back to K. Okay. Sometimes I ramble and then don't actually answer the question that was asked, so. Any other questions?